This video is part 3 of a lecture on section 4.4 from Math 311, a course in linear algebra at Western Illinois University. So we proved the big diagonalization theorem. Well, that proof relied on the fact that this inequality, that if A is an n by n matrix, and whenever lambda is an eigenvalue of A, then the geometric multiplicity is going to be less than or equal to the algebraic multiplicity. And we remind you that by geometric multiplicity is the dimension of the corresponding eigenspace of lambda, and the algebraic multiplicity is the number of factors of x minus lambda in the characteristic polynomial of A. So what we're going to do is we're going to give another sketch of a proof. We're going to prove this just when the case in a very specific situation where we're dealing with a 3 by 3 matrix and the geometric multiplicity is 2. Okay, so we're going, and then hopefully you can get the idea of what's going on. So suppose that A is a 3 by 3 matrix, okay, and and lambda is an eigenvalue of A, and the geometric multiplicity of lambda is 2. Now what we want to show is the algebraic multiplicity is greater than or equal to 2. Obviously in this case it can only be 2 or 3, but we're going to see why that is. Alright, so the geometric multiplicity is 2. That means any basis of the eigenspace is exactly two vectors. So let's let v1 and v2 be a basis of the eigenspace of E lambda. Okay. All right. Now we can easily find, hopefully, we can find a vector w which is not in the span of v1 and v2. Okay. And then that would mean that v1, v2, and w are going to be linearly independent. Okay. We're kind of using this proper whenever you have like a linearly independent set of vectors that can always be extended to a basis of something, but really all we just need one more vector here. So it's still linearly independent as long as it's not in the span of the other two. Alright, and then we're going to let Q be the matrix whose columns are these vectors, v1, v2, and v3. And not v3, but w, right? Okay. And because these columns are linearly independent, this means that Q is invertible. Okay, because of this, and so Q inverse. We're gonna just give Q inverse by its rows. And let's say the rows of Q inverse are R1, R2, and R3. Okay. All right. Now, because these are inverses of each other, their product will be the identity matrix I3, right? So this is Q inverse Q, which is R1, R2, R3 times V1, V2, W. Okay. This will be I3, but if we multiply this, notice that we can break this into we can partition this matrix into a 2 by 2 matrix. We have, if we take the just the submatrix form by taking these two rows and these two columns, okay, this is going to be a submatrix of 2 by 2, and then similarly, if we take R3 and these columns v1, v2. Okay, that will be a 1 by 2 matrix. Okay, And then we'll also have some junk here, here, and here. Remember that to just keep in mind that R1 and R2, these are not numbers, these are vectors. Okay, so we're not, yeah. So this is actually a 2 by 2 matrix, and this is a 2 by 2 matrix, and we're multiplying them. Okay, this would be a 1 by 2 matrix, and this would be a 2 by 2 matrix. So the result's 1 by 2. But because this is the identity matrix, we can see that this is really just going to consist of 1, 0, 0, 1. So this is just going to be the identity matrix I2, and then this is just going to be zeros everywhere. And obviously this would be 0, 0, and 1 here. Okay, but now, so that's one thing to keep in mind. Now let's look at AQ. AQ. So this is going to be A V1, V2, W. And this is going to be AV1, AV2, AVW, or AW. But this is because V1 and V2 are eigenvectors, this is lambda V1, lambda V2, and this is still AW. Okay. Now what we'll do is we can see that this, in fact, is just going to be lambda V1, V2. Okay, this will be a, this will actually be, well, we'll leave it like that for now. Okay. Now let's multiply on the right. Let's consider Q inverse AQ. Okay. All right. Well, Q inverse, this is going to be R1, R2, R3. And then AQ is going to be lambda V1, lambda V2, and AW. Okay. But we said now once again, if we take these two rows and these two columns, we almost get the same thing as we got up here, right? The only difference is we have a lambda here. So what we're going to get is that this is going to be lambda I2, and then here we have R3 and lambda V1, R3 lambda V2, and we saw that this was 0, and if we multiply it by lambda, it's still 0. So this will be 0, and then we have something here which we don't care. The three other elements we don't care about right now. Okay, so this is going to be lambda 0, 0, lambda 0, 0, and something, something, something. Okay. All right. Now let's take the characteristic polynomial of this matrix. It's going to be very easy. Normally we would take, take the matrix and subtract lambda I, but lambda is, we are already saying lambda is a number, so we're going to use x as a variable here. So let's say if we want to take the determinant of Q inverse AQ minus xi 3. So now this is going to be the determinant of lambda minus x 0 star 0 lambda minus x star, and then 0 0 star minus x, whatever that is. Okay. And if we calculate this is going that we can take this determinant by expanding along the row with these two zeros, and we'll get that it'll be this times the determinant of this matrix, which is lambda minus x times lambda minus x minus 0. So this is actually going to be lambda minus x squared times something. Okay. So whatever this will be a polynomial in x, but lambda minus x is going to be a factor, and it's going to be a factor twice. And this is the characteristic polynomial of Q inverse AQ, but because this is similar to A, because Q is invertible, this is also going to be the characteristic polynomial of A. Okay. So the character's polynomial is going to be lambda minus x squared times something. Okay. And actually, this something is really just going to be one linear factor. So this something might have lambda minus x as a factor, it might not. But we can see the multiplicity then of lambda is going to be, and by the way, I should say this is the same thing as x minus lambda squared, okay? Or, plus or minus, really plus, but you can write this. So we can see that the algebraic multiplicity of lambda has to be at least 2, which we assumed was the geometric multiplicity. So that's the idea why this works. We could, if we wanted to replace it with 2 with something else like 3, then we could basically you would do the same thing here. You'd end up with the point here is you would partition extend this to get a square invertible matrix, take the inverse, and then whatever's going to be up here, in this case it would be a 2 by 2, or it could be a 3 by 3 submatrix, but this submatrix is always going to be the identity, and this submatrix is always going to be the identity times lambda. So that's why we're always going to get Q inverse AQ is going to be a matrix like this. So that's the idea of why the geometric multiplicity is always less than or equal to the algebraic multiplicity. And see you next time.